group in hardware technology. His team works on multimodal technologies that bridge vision, language, and spatial understanding. His group has shipped impressive core 2D and 3D perception technologies, including RoomPlan, that I'm very sure most of you people have played around with, and is now advancing Apple Intelligence through cutting-edge work in visual and foundation models. Right.
Awesome. Thanks for the intro. Okay, so I think Laura's talk was a lot about outdoors and cars and self-driving, so we're going to move back to indoor scenes and talk a little bit about indoor scenes. I've tried to divide the talk into 3 pieces. First I'm going to talk a little bit about some of the work that we have done a few years back that leverages a lot of point clouds. Then I'm going to talk about this project that we've been also working on for a few years now called Cubify Anything. That is a work that is a highlight at the CVPR this year. And then later on, I'm going to talk a little bit about areas that we have more recently started looking into that leverages foundation model for 3D understanding. Back in 2012, Apple released the LiDAR sensor in our iPhone 12 Pro lineups. And that kind of provided a completely new way for us and developers to interact with the environment and capture the world. And LiDAR sensor is a time-of-flight sensor that emit beams, they hit to the object, they come back, and the time that it takes for the beams to come back allow us to estimate the distance and how far the objects are from the scene. And this is the source of us getting all the point clouds that we use for processing. So one of the applications that we developed with Apple that leverages this LiDAR sensor that was shipped back in 2022 as part of a third-party framework that developer could use is called RoomPlan. And this is very relevant to the topics that we're going to be covering. So I want to show you this demo that I think best describes what RoomPlan does. Basically, the users start by moving the phone and the scanning automatically starts. And you can move around the camera and you can capture the scene and most room-defining elements in a scene, including openings, major objects, and you can see the cabinets and doors, and the accuracy was excellent. And a lot of it was thanks to our depth sensors. And once the scan is done, you can see the progress also at the bottom in this PIP view that we have. Once the scanning does a series of post-processing models and algorithm runs and create this beautiful dollhouse, which is in a parametric format, and you can do a lot of stuff with it. One of the components of RoomPlan is 3D object detection, which we specifically use to define this room-defining objects in a scene. And it's based on this pipeline that a lot of the classical 3D object detection method, even more recent 3D object detection methods still rely on it. That is based on point clouds. Basically, the way it worked is that we take the semantic point clouds, which is a point cloud and a semantic label associated to the point cloud. We create a wide frustum, and then we pass this into a detector that does this local detection for that specific frustum. And then we accumulate all the bounding boxes for a scene, and we do some further post-processing. We also have a global detector that detects this larger objects like cabinets that can't fit within one frustum to generate the final results. So there's a lot of kind of fusion and post-processing that goes into this pipeline to generate the final code. The data that was used, not the full data, of course, but a look into the data that was used to power RoomPlan is something that I want to talk about, which we also released as part of a data set called ARQ Scene in NeurIPS a few years back. It was one of the first data set at the time that had a large number of scene, it was geographically diverse, and it also used the Faris scanner as a ground truth depth. So we had the handheld iPad Pro with LiDAR sensor to capture the scene, but we're also using a Faris scanner to get laser scanner to get a very accurate ground truth depth. And that was also kind of the spark in some of the other data collection efforts that later on used Faris as ground truth as well. So here's an example of what data we were able to capture with the iPad Pro. You can see we have various sensors captured with the device, and then it's used to do reconstruction, where you can see here. On the other hand, we also use the laser scanner, and laser scanner is placed in various places inside the room to get this very accurate set of scans. Then they are all registered together, And you can see that the fidelity and the quality is a lot better than the 3D reconstruction that is captured from the iPad. And that is technically what we use as ground truth. And then we register the camera poses to the iPad poses and to kind of create this series of RGB LiDAR depth and also the ground truth depth that comes from the Faris scan. So this was kind of like a warm-up topic and a set of work that was a little bit more, older. But now I wanted to talk about an ambition that we always had, was from this room-defining objects to basically detecting anything. And that was something that one of the team members, actually Justin, he's also here, and he has a paper as a highlight on Sunday morning, kicked off, which we call Cubify Anything. And the ambition was, okay, can we actually detect everything in the scene? How far can we push this? Can I detect the little remote control that is here? And what does it take to do that? So here is a little teaser into what that ambition was and the type of kind of data that we ended up collecting ground truth to do that. So you can kind of get an idea about the fidelity of the things in the scene that we want to capture, which I think at a time or even today we are really pushing the boundaries for what's possible. And here's some panoramic view of some of the scenes along with the type of objects that we have in our ground truth or we are able to actually detect. So now let's dive a little bit deeper into this. One of the major pieces of this work is improving our annotations, because we realized that annotating in 3D space and the way that we were doing it before, even on ARKit scene, wasn't necessarily the most accurate way, and it came with its own limitations. For example, here you can see some examples of the labels that were done on point clouds and then back projected into RGB. And you can see that they are not that accurate when you look at it from the RGB point of view. And if you really want to empower RGB to do 3D detection for you, then this is not really going to work. So we were also very interested to see how much we can elevate RGB and have an RGB first kind of 3D object detection. So the first thing we had to address was to fix some of these labeling issues that we have. So we wanted labels that are pixel perfect, accurate 2D and 3D labels. We wanted them to be exhaustive. Basically, we wanted to push and have all these small objects there, and we wanted it to be fast and efficient because it takes a long time to label these objects, so we had to innovate. So the best way for me to describe what we did was to show you kind of a video of the labeling tool that we ended up developing. So what happens here is that the labelers are able to kind of draw a 2D bounding box, and we have a model in the loop labeling pipeline. So we actually use the model that we train on a set of data to help us lift these 2D boxes in 3D. And that gives a seed to the labelers to try to modify and massage. Then our labeling tool also has this ability to kind of give the labelers this multiple RGB views that they can leverage to tune the bounding box and make sure the bounding box is very, very efficient. So this really helped us not only kind of make it easier for labelers to kind of label these objects, but also do it much, much faster. So this was kind of one of the biggest breakthrough that we were able to do, and one of the reasons that we were able to do all of these this bounding box at the scale that was needed to do this work. And here's a snippet into the data that we kind of built and also released, and a comparison with ARKit scene. You can see that we have an order of magnitude more, more number of boxes. We also were able to release more ground truth depth maps compared to ARKit scene, even though it was coming from a less number of sequences, unique scenes, but a number of sequences, but it's still in terms of the 3D object detection, it was significantly more than what we had before. And of course, our ambition is to get to 1 million. So this is the data set we call Cubify Anything, or CA, that I'm going to be referring to in the rest of the talk. So let's look at some of the scenes that have been labeled through the labeling process first, and this kind of gives you an idea about the level of labels that you're going to be able to find in this data set, and how exhaustive the labels are, and how actually accurate they are. This is not just about, again, getting as many cubes as you can in the scene, but you want cubes that are pixel perfect, you want cubes that are exhaustive, and as mentioned, we wanted to do is very efficient. For example, you have this, even door handles, and almost most objects are captured. Again, some objects are missed. I don't know if you guys noticed, there were some toys in this capture. Actually, you can see it right here, that not everything has been labeled in the ground truth. I want you to pay attention to this, because later on, we see that even for during inference, in order to detect everything, we didn't really need to label all of them. But we had enough objects to kind of supervise the model to detect them later. Okay, so let's move on and let's see how does this work actually. On the top, you're showing a more kind of classical, or let's say existing pseudo object detectors, the pipeline that is widely used, even be used it kind of in room plan that I showed earlier. That we have an RGB, we have a depth sensor, we do some downsampling of the input, we do some back projection, we create these point clouds, and these point clouds are used with their very strong inductive biases into some very specialized 3D architecture that leverages, let's say, point-net architecture or 3D convolutions, and then they decode this 3D bounding boxes. The way that we did it was that we wanted to, again, leverage strong BIT backbones that, again, they are also very RGB friendly, and that was also very strong to pre-train them on large data sets. And the pipeline is actually quite simple. We follow architecture similar to 2D object detection transformer-based pipelines like DETR. And you basically take RGB. Depth can be optional, and it comes at a much smaller resolution. We just patchify the image and the depth input. We feed it into the VIT transformer that is initialized either through strong VIT backbones like depth anything or even multi-MAE. Multi-MAE is specifically worth a mention because multi-MAE pipeline is pre-trained on both RGB and depth, and is a great fit for cases where we specifically want to input both RGB and depth. And it's a single scale. It's fairly simple to implement. I want to highlight some of the results next. Okay, so the best way to look at this table is to go from left to right. So first, let's look at traditional SON RGBD block. And on the top, we are comparing with some of the point-based method that I'm sure you guys have heard of it. And there's actually an RGB-only method that we're also comparing with. And at the bottom, we also have the Cubify transformer, or we call it CUDR in short, that we have both the RGB version and the RGBD version. So on the left, you can see the traditional SON RGBD benchmark that it's widely used in 3D object detection. It's only 10 classes, is large objects. And this is where this point-based methods really shine. They start kind of like showing their power, and they can do really well. And you can see that CUDR is not really beating them, but it's still pretty competitive. But CUDR is doing pretty well when we compare with IronBookNet. And then when we go to the second part, which is now we are adding more classes. Like here, we are adding more set of objects into the scene. It's 30-something classes, small objects come into the play. Now we are starting to see the limitations of some of these point cloud-based methods. And you can see that the gap between CUDR, depth pipeline or RGBD with the state-of-the-art methods start getting smaller, and even we outperform them. And of course, when it's talking only about RGB, our pipeline is doing still much better than the best RGB methods out there. But now when you go to CA1M, which is exhaustive object detection, all objects, now you truly start seeing the gap, because again, those methods are not really able to scale to that level of objects and fidelity that we were after. And that's where you can see that CUDR and Cubify data sets can really start kind of showing their value. And of course, on the RGB side, also the gap is getting wider and wider. So in smaller data set, focusing on large objects, CUDR is competitive. By dealing with smaller objects, CUDR start kind of showing its powers and wings. And when we talk about RGB, we are doing still quite better than other ones. Another thing that we wanted to experiment with was that, okay, can we use actually CUDR as a pre-training? Can we use that as pre-training for any other, and apply to other techniques? So as you can see, when you use, not CUDR, Cubify anything data. So when we use Cubify anything for pre-training, we can see the numbers that's been done is on only 3D kind of splits of Sun RGBD, which was the second portion of the table that I showed earlier. And you can see that, even when we use that, even on Sun RGBD, when we use Cubify Anything dataset as pre-training, our numbers even get better. And you can see that there's even 13% improvement or 10% improvement on AR50 for our RGBD models. So an improvements here, what I want to mention is important, is that the improvements are coming from a better box regression that we have in Cubify Anything. It's a data set that doesn't have labels. At least for this work, we didn't use the labels. We only used the box regression. So the effect of having accurate oriented bounding boxes and exhaustive labeling of those bounding boxes is the key in enabling a very strong pre-training data set for training your 3D object detection. Okay, and maybe time to show some inference results for the same scene that I showed the ground truth for. So you can see again, this is just the raw output of Cubify transformer model. You can see that objects that are in the view are detected. Some as the recessed light in the ceilings. We have all the decorative items, the outlets, doors, door frames, and even all the little toys on the shelves are detected. And the bounding boxes, the accuracy is still relatively in line with the ground truth that we have. Here's all the toys on the shelves. And we have this implementation during visualization that we don't show things that are occluded or not in the view. So if you don't see them, it's mainly an artifacts of visualization. Okay. I also wanted to flash this, which is a very, very recent work that we put out a couple of weeks ago, which was a submission to which was a recent submission that we had. And this is using an unposed RGB frames. Just using unposed RGB frames, we basically are able to not only detect the objects, but also solve the problem of localization and mapping at the same time. Basically, you get a set of unposed RGBDs, similar to structure from motion that relies on the key points and matching key points across frames. This purely relies on objects. Now, because you have very accurate bounding boxes and objects, you can actually match them across the scene, and they're exhausted. So can we actually use these boxes and objects instead of the key points and solve that the mapping problem that we have? And if this really works well, which we're showing that it's actually working really well, this can really help us get rid of some of the heuristics that we had in the room plan pipeline for having to merge all the objects together and have a global detector, etc. So it solves the problem of detection, matching, and this global kind of aggregation of all the results together. And it also estimates the camera pose for you that I'm trying to kind of show in the slides here. Okay, so with that, I'm going to move to the last piece of the talk. And I think this is a workshop about foundation models. So we have to talk about LLMs and multimodal LLMs too. And I think this is a great topic to cover at the end. I'm going to talk a little bit about our work, MM-Spatial, which what we are doing here, we are exploring how much we can push this multimodal LLMs, spatial reasoning capabilities using the data set that we just showed earlier. And the motivation for this is, I think it's quite clear. A lot of us are familiar with, if you look at some of the even frontier models out there, when you start asking them some, things and questions regarding to spatial scene and spatial reasoning, the responses that they give you are not really accurate, or it's not necessarily doesn't include the fidelity that you want. For example, they don't really give you the metric distances. They might just give you what's closest to you, and it doesn't really provide anything beyond that. That might be needed for many applications. So our goal was that how much we can actually push that capability forward with the type of data that is public and everyone has access to. So what we did was we first again worked on building a data set, and that data set that we built is actually a data set that is built on top of that Cubify Anything dataset. So now we have very great bounding boxes. We have a lot of them. We also have captions for each of the bounding boxes. Images, we have a lot of depth inputs. Basically, we have ARKit scene inputs, depth inputs. We have the Faro ground truth depths. We can create anchor frames for each reference frame and do multi-view kind of 3D understanding. So basically, we wanted to applet all of these things and see if you feed a depth to a multimodal LLM, if you feed multiple frames to multimodal LLM, and try to do special reasoning, how does it affect the quality of the model? We also wanted to create a wide range of type of questions that we could use during SFT in these models. So we touched upon a lot of these tasks, special reasoning tasks, such as relative special relationships, metric distance. We want to do grounding and referring both in 2D and 3D. We want to do counting, and we also leverage the external benchmark templates and references to make sure that we are not kind of overfitting to like some specific type of questions and be as generic as possible. And then we did a lot of ablation at different sizes of the multimodal LLMs. And the models that we used here is the model that we built in-house, which is based on MM1.5 architecture. And one goal that we had is that we just didn't want it to take a multimodal LLM and SFT and fine-tune it on one benchmark, because then you're going to lose the general capability of multimodal LLM. So we wanted an LLM that is still keeps its general capabilities across different benchmarks, but at the same time has an elevated special reasoning capability. And we experimented not only with different type of inputs, but we also experimented with different ways of using depth. For example, when we want to ask model to predict or give a response about depth, we use chain of thoughts or we use tool use. For example, we can ask the model to go use some of these great tools that we have, like metric depth, to get the depth of the bounding box that you're asking questions about. So we experiment with different ways that I'm going to be talking about in more details. Actually, I'm going to be talking about it in this slide right now. So again, for training data, we use we basically use a recipe that is very similar to the recipe that was used in MM1.5 or MM1, but we also kind of brought in the special reasoning benchmarks into that. So as a result, we created this generalist multimodal LLM that also has a very strong special reasoning capability. So you can see here that, this was MM1.5 3D model, that when it comes to, special understanding, the capabilities were not that great, 40%. But when we add this mixture to it, it's bumped up to like 70. But at the same time, we keep its quality on general benchmark, knowledge benchmark, text-rich benchmark. Also referring and grounding is improved because this data set that we have also has a lot of referring and grounding capability. So let me talk a little bit also about this different applications that we did, because I'm going to be showing it in the table. So we can actually do this applications, as I mentioned, in many different ways. We can change the input to multimodal LLMs. We can give multi-frames. We can give depth inputs, or we can actually have the model to directly estimate the depth and do this chain of thoughts. For example, if you ask, hey, tell me how far the TV is from me, then the model can first say, okay, let me first locate the TV. This is the bounding box of the TV. Let me then go to the tool use and see how far that bounding box is from me. And then it uses basically this chain of thoughts and also tools as optional, available inputs to answer the question. So I wanted to also show some qualitative results. I know that this is very small, so this is the best I came up with. So to turn it into a little maybe video and move it from left to right. So please look at the Q&A and hopefully you see that it's doing something, right? So, questions regarding to relative relationships, referring, viewpoint dependency, dependent relationships, and, basically using your multimodal LLM to do 3D grounding directly from the model, without necessarily having to like build any specific 3D heads or something on top of it. So this is also something that this data set provides. And at the end, I want to kind of show this slide too, that shows a bunch of application that we did on our CAVQA dataset, Cubify Anything VQA dataset. and some comparison that we did with, frontier models like GPT and, by2 Vision, Level 1 Vision. And also we did comparison with special RGBT model that, again, is a special RGBT is also a data set that focuses on spatial reasoning. And we wanted to kind of compare that model with different versions of our model. So you can see the vanilla MM1.5 model is shown here. That's the average number. And then when we compare, and these are like special understanding tasks only. And you can see that the bump that we get immediately by introducing this data set into the training. And you can see that the effect of using chain of thoughts, effect of using depth as input, or using depth tool as input. One of the things that was very interesting that we observed was that if you provide monocular depth to the model as input, it doesn't work so much better than directly asking the model to estimate the depth after fine-tuning it on that data set. So this multimodal LLMs to some extent can actually do this monocular depth estimation for you. And again, the depth tool is something that again helps improve on top of all the benchmarks. But again, the chain of thoughts and the tool use, they come as extra cost that you have to pay during inference. So it might not be desirable for different applications. Okay, so and I wanted to end my presentation by showing this fun video that, again, there's so much more modalities in these data sets, AR Katsine, that we haven't really talked about. We have multiple different camera inputs. You have depth, you can get semantics, you have the IMU, you have the camera pose. There's so many things that, this really should unlock a lot of this multimodal understanding. So we should not necessarily limit ourselves to like just exploring this vision related modalities. So I really hope that this data set can really help us kind of do some research where we can actually leverage all of these modalities together in near future, something that we are also very interested in. Okay, with that, I'm gonna end and take some questions.